This is related rates. Related rates are pretty fun in my opinion. But a related rate equation is an equation involving two or more variables that are differentiable functions of time and can be used to find an equation that relates their corresponding rates. For example, one we're going to do soon is an oil slick. If the radius is increasing at this much, how fast is the area increasing? And the height of a conical cone or the ladder falling down a wall. These can be very helpful for certain things, but you gotta know how to do them to pass your AP exam. So, the steps. If you're given a problem, we'll start out with this problem of an oil slick. We have the radius of an oil slick. It spans at a rate of 2 meters per minute. Now, instead of putting radius, because that's not the right thing you do dr dt. That means the radius
with respect to time.
With respect to time. You are always going to have respect to time if it's increasing at this some rate with respect to time. Always. Because that is what a related rates problem is that over time something's happening. So we know that radius with respect to time is increasing at 2 meters per minute. Alright? We also know, they want to know how fast is the area of the oil slick increasing. So, how fast is the area with respect to time increasing? That's our question mark. When the radius is 25 meters.
Make sure you write everything down because that gets you full points on the AP
The way
exam.
the AP exam is graded is they don't really have exact things that they look for and tell you to look for these. They will look for different things all the time, and one time they might look for just you knowing what you're looking for. So write down everything you learn.
And that'll get you a point or two.
That can give you a point or two, and there's 9 points that can really save you a lot. So the first step is understanding the problem. So we understand the problem that we have our radius increasing at 2 meters per minute. We want to know how fast the area is increasing when the radius is 25 at that instant. So we need to find a mathematical model of the problem. That means drawing it or whatnot. But instead, you can write an equation relating them. So we know that the area of a circle is pi r squared. So it's best to write that down. Area equals
pi r squared.
Pi r squared. So now we need to differentiate that so that we can get it with all these variables. So what happens is when you differentiate a, if you learn how to differentiate, that becomes dA dt equals, now that we have this, the power rule, this is a constant and this is the power, so bring down the 2 and you're going to get 2 pi r. And remember, you just took the derivative of r, so since everything is in respect to time, you're going to need to put down dr dt as well. No matter whenever you take, when you do the derivative of anything in related rates, you're going to have to do it with respect to time.
Volume would be dV dt.
dV dt.
Area is dA dt. All is
A height is dH dt. Just remember that.
It's just all in respect to time. Make sure you do that every time.
So we want to find dA dt. So how are we going to do that with all this going on right now?
Plug it in.
Now we can just plug it in. So we don't know what dA dt is, so let's just keep that going right here. This is the last step, is plugging and chugging. So we have 2 pi r, 2 pi. We know r at 25, and we know dr dt is 2 meters per minute. So once you do that, and you multiply everything out,
you get
100.
100 pi.
100 pi. And that is how fast the area is related to time is increasing when the radius is equal to 25. Now there could be a second part of the question, is that if the radius is 0 at time 0, how fast is the area increasing after 3 minutes? So after 3 minutes, how fast is the area increasing? So we know dr dt is 2 meters per minute. We want to know dA dt, but we don't know the radius. Well, if it's 0 at 0, and it's increasing at 2 meters per minute, 3 minutes later it's going to be 6 meters. So instead of r being 25, we know it's going to be 6. And you can plug it back in here. I'm not going to plug it back in and show you. You should be able to do that if you're in calculus. But 6 times 2 is 12, times that is 24. So on that part, 24 pi would be your area increasing. That's a simple related rates problem, trying to figure out something with things changing over time.
So yeah, just make sure you write everything down and never plug it in until after you've taken it with respect to time.
Yes. So now we're going to go on a little bit more advanced one real quick. One last one. And these are the simple, or actually, I should say the advanced cone problems. So on our left right here is a conical tank. which is very simple, is what normally what you're going to do, is an upside down tank. So I'm going to draw the cone here. Excuse my drawing, I'm not in art. But it says, water runs into a conical tank at the rate of 9 feet cubed per minute. So we know that since it's feet cubed, it has to be volume. So we know what dVdt equals. And that equals 9. So the tank stands point down and has a height of 10 feet. So we know this right here is 10. And a base radius of 5, so this is 5. How fast is the water level rising? So we want to know what dH/dt equals. The water level. We don't know what that equals. We want to figure out how fast that's going up when the water is 6 feet deep. So when the height is equal to 6. So you're probably wondering, it's going to be going up at the same rate no matter what. Well, as you can notice, even if it's going in at the same rate for a cone, it's going to take longer and longer for that height to go up because it's got more and more space over time to go into. So what do? We're finding dH/dt, we know what dVdt equals. So we know what dVdt is, so we need to find out the volume or the thing for a cone. And we know that as volume equals 1/3 pi r squared h. So we need to get we want h. We don't want r, we don't care about the radius. So we need to get r in terms of h. So how do we do that? We know that the radius over the height is r over h is equal to 5 over 10. Since similar triangles, if you know those. So multiply by h, and you're going to get r equals, well, this is 1/2. So h over 2. So best thing to do now is to plug this in now. Because you want to get rid of r. We don't want dRdt in there. So v equals 1/3 pi h over 2 squared h, which equals v 1/3 pi, which is going to be h squared over 4, right?
Yep.
So 1/12, that's 1/3 times 1/4 equals that. H squared, h cubed. All right, so this is the equation we're going to differentiate. I'll write it back over here for people who can't see that. This is going to help us find out what the dH/dt is, right? Height going over time.
Yeah, that's the only exception where you plug something in before you
differentiate.
When you want to get rid of r.
When you're trying to not just r, just trying to get rid of a variable because you don't need it, and there's 3 variables.
In this case, it was get rid of r and plug in another h.
Yes. So we're gonna take this. We're gonna have dVdt equals. Take this down.
1/4
pi
h squared dH/dt.
dt. Now you plug and chug. dVdt equals 9, which equals 1/4 pi. H we know is 6, so 6 squared is 36. dH/dt. Get dH/dt by itself. Multiply by 4, you get 36. Divide by 36, you get 1. Divide by pi, you get 1 over pi. And that is our answer for dH/dt with just a check of the book. And the height in over time is increasing by 1 over pi, or 0.32, about 0.132, or 0.32. And so now we know that it is rising at 0.32 feet per minute. Make sure you put that feet per minute thing, or you will not get credit for it. If they wanted to know how fast the area of the base, since it's a cone, was increasing, you have to put feet squared per minute. If they wanted to know the volume, like dVdt, we knew dH/dt, put feet cubed. You will get points for that. Those are related rates. Hopefully you learned something from this, because I have. But good luck on your AP exam.